Hello and welcome everybody. My name is Luca. I'm leading the research and development of Stampack, and today I'm very excited that we are introducing a new module to the Stampack in the Stampack ecosystem to the American market, and it's called CAPY-Q, and it's about robustness analysis. And so the purpose of today's webinar is to tell you why this is so exciting. And then let's say I will try to make a short introduction to explain why it's necessary, why it's helpful, why it helps you to save money. And then afterwards, I will hand over to Patrick from the company Return on Data. And so the company Return on Data provides this technology, and Stampack is interfacing to this technology. But the software itself is done by CAPY-Q, and Stampack has an interface to this software solution. And let's go. So today we will speak a lot about parameters, and before we take a look on detail, we will try to see what kind of parameters are used in a simulation softwares and which parameters optimize my process, and on the contrary, which parameters maybe do not have any influence at all. And what we want to do in the end is to answer some very easy questions. Can I guarantee a feasibility if I just make one simulation with one parameter setup? Can I compensate the springback of my part? Or is it simply impossible to compensate the springback? And the last quite easy question is, imagine you have good quality material and bad quality material. Can I make all the necessary variations to quantify what is good and bad? Can I do this all manually by just changing the parameters? So these are the key questions that we want to discuss, and the solution to answer this question will be in the end the new module CAPY-Q by Return on Data. So let's start. Which parameters optimize the process? And a process parameter, this is a parameter that we, as a tool and die maker or as a stamper, that we can control. So for example, we can control blank holder forces. We can control the draw bit height. We can control, here it's written spacing, but I think the American expression for this are the bumpers. So how much space is between the blank holder and the die. We can control the friction. So, and in the end, it's quite easy to say what will happen. If I have too much blank holder force, okay, my part will have a bad material flow, and I will have cracks. If I have too little blank holder forces, then we will have wrinkles and low stretch. With the bumpers, it's the opposite way. Where if I have two large bumpers, then we have wrinkles and low stretch. And if they are too low, or if I don't use bumpers, maybe I'm going to have cracks. If the draw bit high is too high, the part will crack. And if it's too low, then we will have wrinkles and low stretch. And we all know low stretch means an uncontrollable springback. And also for lubrication, it's quite easy to say too much, then we have low stretch, too low, then we'll have not a good enough material flow, and we will have crack. So qualitatively, it's very easy to say what happens. But I mean, the parts you guys make, they are really difficult and complex. And in the real world, it's very difficult to say which parameters are improving the process. Which parameters should I adapt to really make a difference? And it would be amazing to know to say, okay, when I change the draw bead height, then feasibility is influenced by 66%. Friction also has an influence, 18%. The bumpers have just little influence, just 12%. And no matter how I put the blank holder force, it will make almost no difference. So from all the process parameters we have, we would like to know which parameters make a difference. And we want to know this quantitatively so that we see, okay, we need to adapt the draw bead height. We need to adapt the friction, but adapting the blank holder force is of no use in this process. So this is the key when we want to learn which process parameters we want to modify. There are another kind of parameters, and these are the so-called production parameters. Production parameters are typically material parameters, and it's very difficult for a stamper or a tool and die maker to influence the production parameters because, I mean, you get the material from the coil and you have the material you have. So, for example, if someone wants to make a part, IC 300, so this is a typical stainless, then you all know that the range that this material can have is huge. So we know that yield strength is greater than 190 megapascal. So this is in the norm. In the norm statement, it's well defined, but typical values are 330 megapascal. Tensile strength can range from 500 to 700 megapascal, and a typical value could be something like 660. Elongation at break is according to the norm for larger than 45%. Yeah, but in real world, it's typically much larger. It's 55%. And even the sheet thickness is not well defined. So when you have a sheet of thickness 1 millimeter, it could happen to you that in real world it has 1.05 millimeter. So plus minus 5% is a typical variation of a coil in sheet thickness. Also, I mean, there are other production parameters that are very difficult to control. For example, the initial position of the blank, because it depends on the locators, and also the friction coefficient. We cannot influence it too much because somehow it always vary a little. And so when we speak about production parameters changing, we have to know we have to ensure feasibility across the entire range, and we have to be in tolerance over the entire range. So this is a huge difficulty in real world. I mean, especially if your company is, for example, once producing in the United States, then they have a factory in Europe and they have the factory in Brazil, and you have to guarantee feasibility over all factories. Yeah, then you have a huge problem because the production parameters can be totally different. And so far about the parameters, and now we would like to speak more about what has simulation to do with these parameters. In the end, what about the easy question? Can I guarantee feasibility just making one simulation? The typical way how people did this is, let's say they had somehow they put a limit, let's say 80%, and they said, okay, I will not design the tool and my process in a way that I'm below 100 in feasibility value. I design it in a way that I'm below 80, yeah, to have some safety margin left. But to leave some safety margin just to cover variations in material and production parameters, yeah, it's a huge safety margin. And let's say this results in a simple fact. Processes that are designed in a way that the feasibility value is below 80%, this means that the process is not optimal. So not optimal could mean we could have more stretch to be more stable in springback. Not optimal could mean that, for example, in a progressive die, we could save another station, and saving a station is a huge cost saving. So it's much better when we can come closer to the 100 to leave less safety margin. But if I want to get closer to the 100, like what we see here, the 92 feasibility value and 100 is crack, then I need a tool that quantifies the variations of the process parameters, because otherwise, let's say I have a risk on my side. Also a question, yeah, that is really important for for every tool and die maker and for every stamper is the following. Does it make sense to compensate the part? Do I get a part within tolerance when I compensate the springback? Or is it simply of no use compensating the springback and I have to first modify the process and then compensate the springback? And my claim is the following. A component is only compensatable if the springback is stable. Because if in one part the springback is 1 millimeter in one direction and in the next part its springback is 1 millimeter in the other direction, then it's simply then the variations are too big and I can never be in tolerance. So if the springback varies by more than 1%, never you will be in tolerance of plus minus 0.5. No matter what you do, no matter how you compensate the springback. And here I have again an example of my stainless steel. I have here tensile strengths, 670 megapascal, thickness 1.15 millimeter. And then you see here I'm away 0.3 by I'm 0.3 away by the nominal. And if I go on the lower range with a tensile strength and on the upper range with a thickness, then I have here minus 0.7. So I have here 1 millimeter deviation. And no matter how I adapt, let's say the geometries, for example, if I modify the geometry in such a way that I have here 0.0, yeah, then I'm here in this variation, I'm here more than 1 millimeter away. Yeah, whereas here in this area, the change of the production parameters, the change of the material parameters has absolutely no influence on the springback. So the springback here is 1.1, here is 1.2. So it's very stable, and in this area I can compensate. Because in this area I will put the geometry 1 millimeter upwards, and then I will have here a deviation of 0.1 and here 0.2, and I'm fine. So bottom line is we need a technology that quantifies my variations. And only if the variations are small enough, then I have the chance to compensate the springback to get into tolerance. I mean, of course, there are possible solutions to this. So you can purchase material with a tighter tolerance. Yeah, this is expensive, but you can do this. But also here, you want to know which parameter is relevant. Yeah, do I need to have a smaller range in tensile strength, or do I need a smaller range in material thickness? And we need a technology that answers this question. And of course, the second solution that is always good is if you introduce more stretching to the component, and typically then the spring back gets more stable. And finally, is it possible to make these variations manually? Yeah, so for example, once a customer told me, typically when I have production parameters that vary, then I make one simulations on the lower end, I make one simulation on the upper end of the range, and I make one simulation in the middle. So for example, I make here a simulation with a thickness that is -5%, I make one with a +5%, and I make a simulation with the thickness itself. Okay, then I have to make 3 simulations to cover the thickness. Okay, I have to make 3 simulations to cover tensile strength, 3 simulations to cover the yield strength, 3 simulations to cover elongation at break, 3 simulations to cover the hardening behavior. And already from just varying the process parameters, we would need to make 243 simulations. If we additionally want to vary also the process parameters we spoke about, so blank holder force, again 3 simulations, draw bit heights 3 simulations, friction 3 simulations, and then the bumpers 3 simulations, then yeah, the number of necessary simulations is so large that I cannot calculate this by heart. So we need almost 20,000 simulations to cover just 9 parameters. And the technology that Patrick from Return on Data will present to you in what follows just needs 3 simulations per parameter. So to cover all these 9 parameters, you just need 24 simulations. And I mean, a simulation take maybe half an hour or 1 hour. And then, yeah, you are done in 12 hours. So this is overnight. You can answer the questions I spoke about. Thanks a lot from my side. Yeah, I will stay in the webinar, and after Patrick's presentation, we will have a question and answer session, and there we either Patrick or me, we try to answer all the questions you have. Thanks a lot from my side so far, and I hand over to Patrick.
Thanks for the introduction, Luca. I will try to share my screen and tell something about me. My name is Patrick Aggert. I'm co-founder of Return on Data together with Christian Schwartz and Reinhard Mauermann. They are also in this webinar. Today I want to show you something about our software solution, CAPY-Q.form. So what is Return on Data? We are a specialized company for analyzing industrial data solutions. All of you heard about KI and American AI solutions, but the major problem of AI solutions is that they have a lot of data to train the models. In industrial analysis, we don't have that much data. We need to be very, very effective. So we are developing a mathematical core called the CAPY core that is able to analyze in production data, FEM, sheet metal forming data, even tabularic data, or in future or near future, we will also be able to make volume modeling FEM analysis. We are specialized in software for technicians, so you don't need a mathematical diploma or something like this. We try to make everything very understandable, very easy to use. I will show you next. What's the major unfair advantage of our company? Luca already said we only need 3 simulations per variable. with our algorithm, we are able to make very, very high complex models with this low level of variables. And we have a very big experience. We have solved about, I don't know, maybe 100, 150 problems with our algorithm till now. And so we are proud to got it in our company. We always start with a sensitivity analysis. This means we make a variance simulation, checking the sensitivities of a part. After the sensitivity analysis, you can exactly look which inputs have the biggest effect in which area of the part I want to optimize. When, of course, you can do an optimization. Yes, you can check for the optimal parameter setting. And when you have to do a robustness analysis, Luca already told about it. So maybe just for the guys who have never worked with something like this, I make a very, very easy overview just to make you give an overview what we are doing. If you play soccer, you have a field of parameters that makes it possible for you to hit the goal. Yes. And you can move around the complete field and looking for the best position to hit the goal. So after we know it, where's the perfect area to hit the goal, we know, okay, if I'm kicking absolutely linear, I can shoot from here or anywhere else in the capable parameter settings. My personal problem is that I can't shoot like the arrow I've shown here. If I shoot a football, it looks like this. Yes. Sometimes it goes a little bit to the left side, a little bit to the right side, half the time maybe into the goal. If we want to produce anything, we won't to stay here, okay? Because half of all settings we do will be failing. Yes, we want to stay here and we want to shoot here because in all the cases we are sure that we have a robust design setting. We are always hitting the goal. And this is what we do. Again, something Luca already told you about it. Here you have the failure curve. Yes, it's the form limit diagram. This is the failure curve. Every minor or major strain that goes over this failure curve means you have a crack, you have a problem. So it's common that you have a safety barrier. It could be at 80%, it could be more, it could be less. It depends on the company you're working for. And you are only calculating to the green line. The formability of a part marked with these red lines is not used by you. And these lost opportunities to make a good part is wasted money because you make changes that you don't need. So what does CAPY-Q do? CAPY-Q is reducing this gap between the safety barrier and the failure curve. We are checking for the optimal design. Now let's go a little bit more in the detail. What are the correct advantage or the use for you? Expecting you have a new part. This could be a front flap. Yes, this is driving direction, driving to left side. Here's the right side frame. Here's the left side frame, the front end. Here's the front window. And now you have a part and you want to find out what's the optimal combination for my beads and my blank holder force. So maybe you start with one iteration and you did a lot of iterations. I worked with a guy who gave me iteration number 56. Yes, this means he created 56 iterations of simulations, and checking again and again will be my result into tolerance. And anytime you're in tolerance. This needs a lot of time, a lot of manpower. And what we want to do is to give you a possibility to just by the series simulation, give us the possibility of a possible range that your process parameters can have. And you will get the optimal design automatic, as Luca said, during 12 hours. Next problem is the material problem. Yes, if you're generating your methodology for forming, most people use the mean value for the material. Yes, and if you use the mean value, you're getting a perfectly green part. You're totally happy. Dimensional accuracy check. But when you have a problem, okay, we have minus 10% of the process parameters. Okay, this part is not that good. And if you have additional the other direction, you see, oh, here now you have a problem on the opposite side. You can't do anything. This is not usable for you. I told you a lot of mathematics and statistics. Now I want to show you our easy tool. Okay. Of course, I will show it to you live in a few moments, but I just want to start with an overview. So how to use CAPY-Q.form in the future. It's very easy. You just select the solver file. It's the .dat file you are generating by during the simulation. I will show it to you here. Yeah, here. Yes, you all know Stampack, so I won't go into detail. But if you go to the solver manager, yes, here you have already finished your process. You have a possibility to make the solver file. Yes, and this solver file includes all the information the solver uses to calculate your model. And we just select this solver file. It's called point.dat. And inside this solver file, we find all the attributes you can manipulate. In the next step, I've prepared it here. You take the selection of a work directory. Yeah, now you can decide where you want to do your simulation. What do you want to do? Next is you can choose to make a process analysis, or you can choose to make a robustness analysis. Yeah, in some cases you just want first find out, is this part I want to produce producible? Yeah, then you only look for beats and distances, or is it robust? So you can decide here for robustness and process parameters. And of course, you can select and deselect all the parameters that are available in the specific .dat file. Automatically, you get a number of simulations that are needed. Yeah, as I said, you don't need to think about anything that is very important in here. You could manipulate everything, but if you don't know what to do, just leave it and you will always get a good result. And next you start, you're generating a project directory, you're generating everything, and we can start with a solver calculation. In addition, so that you don't need to leave our software, we added a solver manager. In this solver manager, you could start the simulation. They are running through all the designs we need to do. Of course, if you click anywhere here, you see the result file. You can take a look. You can scroll through it. You see how far is my actual simulation. What else is to do? Additionally, we have two buttons. They're very interesting because if you do a variance simulation and you need 12 hours, there's maybe a very important project and you need to calculate it now. So what are you going to do if you have only calculated 9 or 10 simulations till now? So you could stop the simulation. You could stop it slowly. Yes, this means the actual simulation will finish, and when we make a break till you start it again, so you can calculate your actual very important project. Or of course you can stop immediately, maybe because it's so important that you can't wait till the actual simulation is finished. After you calculated everything, you can take the result files. We automatically give you an overview of the result files. These result files are automatically done by Stampack, provided by Luca, and we give you a selection that which kind of which process step you want to import. Yes, in this case it's OP10, OP20, or the springback for the part. That's all we do in the simulation. Now we are closing this step. Now everything I showed to you is pure mathematics, has nothing. Oh no, one step more. This is still simulation, sorry. Now you finally you get an overview of your simulations. Yeah, here on the left side you see the simulation you have done. And you can click through the simulation and you see the results you get through the simulation and the parameters that are needed to these results. You can get an overview over the range of all simulations, the minimum values, the maximum values, and so on. And when you create a model and when you leave the FEM world and go into the pure mathematical way. Next step. Now we are in the sensitivity analysis, as I told you on the start. Now we have a very interesting possibility. You can take an annotation and click anywhere on the part, and for this area of a part, you're getting the information which parameter is very important for this area of a part. Yeah, if you toggle over the part, this columns will switch. I will show you later, and you get information which parameter is important for this area. And in addition, you get an information about the prognosis error. Yeah. So if you're going over the part, and we are now looking for the failure criteria, our mathematical model can do a prognosis with an uncertainty of 0.5% of a failure. Yeah, this means nearly nothing. It's totally irrelevant. Our mathematical model fits perfectly to the results. Then, of course, now we know our model fits perfectly. We can optimize it. Yes. In this case, we can have sliders for all the parameters we have looked for. And now we can optimize our part and take a look, okay, which parameters do we have to choose to get the failure inside a good range? This means below 100. And so we know, okay, it is possible to produce this part without failures. And finally, we talked about it. Now we know we can hit the goal, but is our actual position where we're standing capable to hit the goal every time? We do the robustness analysis. During this robustness analysis, we make about 10,000 simulations. If you want, you can do 20,000 simulations. One moment, 20,000 simulations, this will need 1,000 years. No, we do it on a pure mathematical way. This 10,000 simulations on your standard PC, I don't know, Core i5, Core i7 Pentium processor needs about 1 minute. Okay, so you do 10,000, 20,000, 5,000 simulations in 1 minute on a mathematical way, and you get an output how robust your process is. And this I want to show you on a very easy example. Yeah, we take a look here. We talked about the 80% limit of a failure. Yes, this is the regular way. You would produce this part, and we say, okay, 80% is the upper limit. Yeah, if you take a look here, we have changed the thickness about 5%. We changed the Young's module. We changed the anisotropy. We changed the yield strength, the tensile strength, the uniform elongation. We strengthened the position of a blank and the distance between blank holder and die. So we have a lot of varying processes inside. Okay, things we can't control maybe. Yeah, we change all of these, and now we see, okay, our process is not feasible because we say 80% limit. Sorry, we need to make a very, very expensive change of a tool. So what if we take a look for 95% upper limit? Okay, now we know all possibilities that could go into the quality of our part are already recognized. Okay. We have already checked all the variations of the parts and so on. We have checked everything, and we see, okay, with a level of 95%, we still have a scrap rate. Scrap rates means of 10,000 parts, 8,831 will be scrap. Oh, okay. Maybe this limit is still too low. Let's take a final look with 98%. 98%, this means our design is nearly to the FLC curve, but it doesn't matter because we already recognized all the variations that could happen to our process. And we see we have a scrap rate of 0%. What did we do now? We have checked that recognizing all variations that could possibly influence our process will lead that we have a good process where no part, if we produce 10,000 of them with different combinations, no part will have a crack, because we don't have this very expensive security gap. Yes, I'm talking about this security gap. This leads us to make a lot of cost-intensive changing loops. Okay, this was very theoretically. Now I want to show you all of these live. Let's go here. So, again, you already know this example. I want to show you some functions that you can handle. Yeah, we are selecting, for example, the .dat file. Yeah, you can select the directory, and now we can change between the process analyzers. Yeah, you see we handle only these process parameters. We could manipulate as we will. Or we can just checking for the robustness analysis. These are the things we can't really change. Okay, this is God's given, you could say. Okay, here you have, of course, the possibility to manipulate all of these, but you don't need to. I am personally not a friend of changing the friction, because with friction you can destroy or make everything good. So, but you have a possibility, if you think it's important for your process, just change it. Even the Young's modulus, yes, you can change it, but looking to your material cards, it nearly never changes. So it's standard, no, but you could use it if you want. Just click yes, and you can manipulate it. This is the reference. The reference is all the values that are inside your basic simulation. That is the .dat file you have selected. You can't change. Yeah, but you can change the minimum and the maximum. Yeah, if you know from your deliverer of your material, my thickness variation is never below 1.2. Yes, let's say, okay, it's 1.2. Okay, no problem. You can maybe change everything. Yeah, as you like, just manipulate it. If you go to the solver run here, I just click fast over it. Yeah, you have a possibility to look in all the report files, checking for the actual state of the simulation. It will scroll down automatically, so you can take a look. Okay, how far is the individual process? And when we go to the model creation, this is one very important step. Here you have a possibility to select all the parameters you have, you can, all the output parameters. Yeah, of course, in the bottom dead center, it doesn't make any sense to look for the distance to reference, because we are in the bottom dead center. But for example, we can look into the failure criteria. And here we have the typical possibility. We can look through all the designs and look. Yeah, here maybe I will show you here what's the variation over the processes, what can we do, or what will change over all the parameters. Of course, you can take a look for the range. Here you see the variation over all designs. This means the lowest value over all simulations to the highest value over all simulations. So you know, okay, in this case, oh, sorry. In this case, in this area, we can make a variation of nearly 30% in this area, and we can have a change of 21% in this area. Okay, so we know, okay, we maybe have a problem with a failure, but we can handle with it because we have a possibility to manipulate it. Now we're generating the model and going to the sensitivity analysis, and I love this example because it's something very special. The influence of a parameter is not as expected. If we now take the annotation and we go over the part, please take a look here to the columns. Yeah, we change depending on the position. This means Maybe you have a geometrical problem or not a failure problem or anything. You can go to the area with a problem and you see the most influencing parameters overall the part. And now if we take a look in this example, and this is very, I like it, we see one moment and no one expected it. The displacement in Y is the highest influencing parameter for this example. I could imagine that no one of you could expected this. Yeah, of course, if you know it, it's no problem. It's the displacement in Y here, bottom right, you see Y direction is this area. And if you are moving the blank 3 millimeters in this area, the blank is sliding over this radius and the material flows much better. And so you have a possibility to reduce the thinning in this area and the failure criteria goes low. Okay, so the other parameters are very less relevant for this area. Something you maybe won't check regularly. So now I want to show you another option. I know some of you have some managers and you want to make a good PowerPoint presentation over your results. When you have a possibility to make everything clean, yeah, take a good position, a good PowerPoint position to make snipping, and when you could Z this view. Yes, now I Z this view. And now in the future, all other figures we're generating could be resetted to this view. I will show it to you. Okay, now we can optimize our part. Again, we want to optimize the failure criteria. Here's our part. I reset to our favorite view. And it's just a zoom thing, yes. And now we can optimize. Okay, we know out of our sensitivity analysis, the displacement in Y is very important. So we're checking if I lower it down, if I rise it up. Oh, if I rise it up, the failure criteria, I set a annotation on it. The failure criteria is lowering down. So maybe we can take an additional look for the forces. If I raise the force, oh, it will go a little bit more down. And if I take a look for the initial force, has no influence. Okay, the initial force doesn't matter. It's the final force that's important. Take a final look for the distance. Distance, making the distance a little bit bigger is better for the failure criteria. Of course, the material can flow a little bit better. Okay, so now we know our optimal process parameters. And if we take this optimal process parameters, I can go to the robustness analysis. Put these parameters into the robustness analysis. I've already done it. Yeah, if you take a look here, yes, this means displacement Y on maximum, forces on maximum, and you can put it in here. One moment, why did I write 2.7 and not 3 millimeters inside here? This is something to do with our mathematical model. A mathematical model is much uncertain on the corners of a model. Yeah, this means we don't like to make any prognosis on the borders of our mathematical model. So in robustness analysis, we go a little bit, a slightly bit in the middle of our parameter range. This means it makes totally sense to make the range of all parameters here a slightly bit bigger when you want to analyze it in the end. But this is very deep. We will discuss maybe this later. So now I have defined everything. I can define my limit. I've done. I lowered it down a little bit, of course, just for make it a little bit speed up. Yes, but now you can take it, look for your clock. I now do the robustness analysis. I'm working on a Core i5. 8th generation. It's an older one, and yes, it was maybe about 5 seconds. Yeah, and maybe now it's still beyond 1 minute for 5,000 simulations. that are done in the background of in the background, and now the analysis is running. And of course, we now need to wait a little bit longer. As I said, it won't take more than a minute, I think. Yeah. Okay. Just to take okay, maybe I was. Let's wait. Let's wait this moment. One moment. Check. So here we are ready. 5,000 simulations done in beyond 1 minute. And we see, okay, with a 95% failure criteria, we have still problems. And as I have shown you in the presentation with 98%, we don't have this problem anymore. I want to give you one additional information, and then I would start with a question and answer session. We could also changing the height of the beads. Yeah, but this needs one special step you have to prepare. If you go to Stampack, yeah, here we have a simulation. It's the hood I've already shown to you. Here we have the beads, and we want to change the heights of the beads. Inside of Stampack, we have no differentiation between a die or a bead. Yeah, so we can't identify it on the .dat file. So in this case, if you want to manipulate the height of a bead, yeah, it is needed that you give the name a bead and a bottom line in front. What you write behind doesn't matter for us, but if you want to change a bead, please write bead underline, and when you can manipulate it inside our software and make additional analysis in this area. Okay, this was a lot of information very fast. I hope not too fast, and I'm quite interested in your questions.
Okay, thanks a lot, Patrick, for going into that detail. I'm really curious about your questions, and I think it would be good if you could write them to the chat, and then we would be glad to answer them one by one. Maybe until the first questions are there. So accurate die design software will distribute this together with a Stampack. So yeah, so all of you can get this product from accurate die design software. So there is a first question of Josh. Do you want to take it, Patrick?
Yes, I take it. When you do a soft stop, it will, or slow stop, it will finish the actual calculation. Yeah, let's let it be the 9. And if you play run, it will start with the 10 and you lose no information. If you press hard stop, it will immediately kill all Stampack simulations on the machine, and you need to recalculate everything of simulation 9 you have simulated till then. Yes, so hard stop means hard interruption. You need to start the specific stopped simulation again from the complete start. Slow stop means it's calculated finished, and you can start again if you have time the simulation 10.
Okay, the next question by Alex Jackson. Does the CAPY-Q.form only support shell simulations at the moment, or will it also work for solid simulation as well? Thanks a lot for this question. So we support both shell and solid simulation. There is only one thing that we cannot do in solid simulation at the moment. We cannot vary the thickness of the sheet so far. This will come in future versions of CAPY-Q. But beside this, all parameters are available both for shell and for solid. So another question by Marco Cavasso. Is the software already translated in different languages, or is it ready for translation? Patrick, do you want to take the question? It's coming from Italy.
Actually, it's only available in English language. Till now, no one asked us for any translation. But if it would be a big problem to use it in Italy, we need to go in a deeper talk how we could make it readable for Italian customers. Actually, it's only available in the English language.
Okay, I hope, Marco, this answers your question. Next question. Does the software have a material library that includes all the upper and lower limits for the mechanical properties? This is typically not always available. So first of all, so that's a great question. First of all, I mean, you have the material library in Stampack. I mean, all the things you do in CAPY-Q are based on a Stampack simulation. So let's say the reference parameters that we see here on Patrick's screen, they come from Stampack. And so then there are two possibilities. So either you get some information from your supplier. So for example, typically for tensile strength and yield strength, there is an upper and a lower. Or what you can also do is to say, okay, tensile strength, I take plus minus 10%, or thickness typical value or the default value is plus minus 5%. Let's say these are values to the best of our knowledge, I would say. Then let's say you cover at least a sort of standard range around the reference value in Stampack.
What you see here is a recommendation we always give, but it's very easy. It's plus minus 10%. Yeah, in some cases it's plus minus 5%. It's automatically filled, but of course you can change it. It's not easy to make here a standard because it hardly depends on the deliverer of your material.
From Josh, when analyzing the results, there looked to be a result type to compare the simulation to a target. Is this the same CAD target that we import into Stampack? So yeah, yes, it is, Josh. So there is the how is called, Patrick? Maybe you can show it.
I've changed the model just to answer this question. For springback states, yes, SPR states, you have a possibility to look exactly for this. It's the distance in nominal and Stampack. This is the result you have imported into Stampack. This is exactly the same result as you see in Stampack. Yes, distance to nominal. This is only available as it is in Stampack if you are in a springback step. Yes, if you are taking a look for a forming step, this is just not available. When we compare to the reference, this is design 0. But in addition, there's a possibility we have included. If you forgot to import the CAD data into the Stampack project, you have done all the simulation, you waited 12 hours, and you see you forgot to include the Stampack nominal CAD data, you have an additional possibility. I want to show it to you. Yes, we have checked all the designs and we have calculated all the designs, and when we can go here for the result import, and here you can select another reference. The standard is that our software uses design 0 as reference. It's just for us as a reference value because we need a reference to look for. You could also add in here just by D-click and select STL file. Just the STL file of any CAD, and then this CAD file will be the new reference. Yes, so both is possibility, or 3 things impossible. Comparing to design 0, comparing to a imported CAD in CAPY-Q, and comparison to the CAD you already defined in Stampack.
Patrick, can you take the question?
Yes. No, we are hardly working on the technical documentation. We hope we get it finished during the next month, hopefully faster, and we will share it as well as the reference as the references I've shown to you today. We will make a package for the resellers available to have anything that they can show to the customers.
And to the second question, Marco, we launched the product in Germany 2 months before, and so we have at the moment 3 active users on CAPY-Q, and it's going really well. So especially for automotive industry, it's a big plus.
Okay, thanks.
Patrick, do you take the next question?
Yes. Does CAPY-Q have a report generation feature to include all results as PDF format? No, actually not, because actually we don't know what the customer really wants, and there's no standard for these management reports. So we decided to make it possible to do easy screenshots. Yeah, just by make it possible to set and reset the visibility, and if it's useful to move this side column outside the window. Yeah, in this example, we decided don't to make it outside the window, because this result only makes sense if you know which parameter we have chosen to generate it. Yeah, but if you, for example, looking here for this, here it's no problem to make it clear and make a nice looking screenshot.
Next question by Ezio. Is it possible to load start from a simulation already computed by Stampack? Yes, it is. So whatever you calculate here inside CAPY-Q, you can open also in Stampack, yeah, for example, to see the forces and the details about the simulation, and also so when a simulation is done in Stampack, you can also launch it here from here.
Yeah, it's recommended. It's strictly recommended that you make a first simulation with this reference values and complete it. Because if you have here a bug, or you have some forces that could make a good result, not nearly a good result, you have very big problems in future designs. So the first design should generally feasible. Okay, it doesn't have to be perfect, but it needs to be generally feasible, and then start with this general feasible design and make the sensitivity analysis. So recommended, simulate this design first and then start CAPY-Q.
I mean, typically this product will be used at a later stage. Let's say, I mean, for early feasibility, let's say it's not recommended to use CAPY-Q. Yeah, but when you are basically happy with your process, and you want to go production, then it's very good to let's say to double check in CAPY-Q. Any further questions or remarks? Then I would like to thank you all for attending today's webinars, and yeah, if you have questions or remarks, then I would recommend to contact Ray. He can organize a demonstration, yeah, for each of you, and then in this case, I think either me or Patrick will join, and then we can look into your own parts together. Thank you so much for joining, and I wish you a great day. Goodbye, everybody.
Also, thank you from
Goodbye.
me, from my side.
Bye-bye.
Bye-bye. Thank you.
Bye. Thank you.